So very good evening to everyone. Welcome to today's live interactive session on geosynthetics and reinforced soil structures. So we are having this today's session after a long time, after a gap of about a week, because we had to do some readjustments due to some personal commitments which I had. So today's session will be mostly on the sixth week lectures, and on tomorrow again we are going to have another session from the usual timing of 3 p.m. to 5 p.m. and there we will be discussing the seventh week, whatever we discussed in the seventh week, all those things we will be seeing tomorrow. Okay, so today's session will be mostly on the week 6 discussion, and tomorrow from 3 to 5 we will meet again. There will be dealing with the week 7 discussion. So these 2 weeks are relatively shorter, like the amount of content is relatively less. So in today's discussion what we will be doing is that we will be solving initially a problem regarding the reinforced soil wall design using geogrids. Okay, so in the previous session, in previous discussion, we actually saw how to design a wraparound geosynthetic or geotextile wall, and we solved some problems, solved a problem from that, and we then saw some more similar problems, right? And in today's session what we will be doing is that we will be starting our session by solving a similar problem related to the design of reinforced soil wall using a geogrid. Okay, using geogrid. Okay, and after that what we will do is that we will solve after that we will solve problems regarding that those embankment, how to calculate the stability for the embankments and all those things. Okay, so let us start today's session. So we begin today we begin our session with this problem, right? So as we see we are asked to design a 7-meter high geogrid reinforced wall where the reinforcement spacing must be around 1 meter. Okay, why 1 meter? Because the wall facing is of the articulated precast concrete type of the same dimension. Okay, that means what? The blocks that we are using, these particular blocks that we are using, these blocks are of precast type. So these are casted somewhere else, precast, and then directly transported to the site, right? So these are precast concrete type, and these blocks have a fixed dimension, right? A fixed height of around 1 meter. So what we need to do, we need to limit our spacing to around 1 meter for that purpose. All right, done. The coverage ratio is 0.8. So what is the coverage ratio? So the geogrid actually, it means that the coverage ratio is not 1, it is less than 1, it is 0.8. Means that the geogrid at each height, at one height, say at any height, the geogrid does not cover in the out of plane direction, it does not cover the whole length of that in that direction. Okay, there is some gap between the geogrid because it doesn't cover, right? Because they are slightly separated. So that's why we need to use the coverage ratio. Okay, in the out of plane direction the geogrids are slightly separated, right? So that's why we need to use the coverage ratio. The length to height ratio of the reinforced soil wall should not be less than 0.7. So this is a condition that is given to us. The length, that is this length to height. The height is height, that ratio should not be less than 7 point. So minimum 0.7 we have to consider. Okay, the minimum length to height ratio of 0.7 we need to consider. Okay. Additional details are given in a diagram below. Okay, so what are the additional details that are given to us? So we can see a surcharge of 15 kilonewton per meter square that is acting on the top, right? So surcharge of 15 kilonewton per meter square, it is acting on the top, and the properties of the reinforced soil are given. So the reinforced soil friction angle is 32 degrees, and the unit weight of the reinforced soil is 18 kilonewton per meter cube. All right. The height of the wall is required height of the wall is given 7 meters, and then we have the properties of the backfill that are given. So the friction angle of the backfill soil is 30 degrees and the unit weight is 17 kilonewton per meter cube. The properties of the reinforcement are also given. So you can see TUR means the ultimate. Okay, ultimate. The T ultimate is given as 160 kilonewton per meter, and then we have the cumulative reduction factor. Okay, cumulative reduction factor is 4. Then we have the allowable as 40 kilonewton per meter cube. Obviously 160 divided by 4, we will get the allowable as 40 kilonewton per meter, and then if we again divided by the factor of safety, we will get the required or the design strength, design tensile strength of each of the geogrids. Okay, we get the design tensile strength of the geogrid, that is 28.6 kilonewton per meter. Also we have one interaction factor is given 0.75. The interaction factor is nothing but we will see whatever it is in the later slides, or while we solve the problem you will see what this interaction factor is, CI. The bearing capacity of the foundation soil, the bearing capacity of the foundation soil, that is also given to us, which is nothing but 600 kilonewtons per meter cube, or meter square, sorry, 600 kilonewton per meter square. That is the bearing capacity of the foundation soil, that is also given to us. Okay, now let us start solving the problem. Yeah, so see, first this yeah, this T allow is what? T ultimate by cumulative reduction factors, right, which is nothing but 160 by 4, we get 40 kilonewton per meter, which is nothing but the T allow, right? Now what is the T required or the T design? Is nothing but T allow by the factor of safety, 40 divided by 1.4, we get 28.6. All right. Now first, now what were the steps that we followed in the previous session? What are the basic steps that we need to do to design any reinforced earth wall? It may be geosynthetic or it may be geogrid, whatever. The main basic concept remains always the same, right? The main basic concept always remains the same. So what we need to do, we need to ensure that our system is externally stable, or the overall stability, and also we need to ensure that it is internally stable, right? The stability of the system needs to be checked. So we need to ensure that our system, whatever we are designing, that is stable, right? So first we have right. So external stability, so for that we need the active earth pressure coefficient for the backfill. Okay, KAP is nothing but 10 square 45 minus 5p by 2, but 10 square 45 minus what is 5e, it is given as 30, right? Given as 30, come out as 0.33. Therefore so see, so now we need to calculate the lateral earth pressure. So one lateral earth pressure is a triangular variation which is coming from what? Which is coming from the weight of the backfill, and another is the rectangular variation of earth pressure which is coming from the surcharge, isn't it? So we will write both those. So P1 so half to 17 . be 34.65. Okay, so this, so this is something P1 and our P2 will be something like this. What is this? This is H by 3. This height is H by 2. Okay, now therefore total force, so will be 172.9. Okay, so we calculated the total lateral force. Now what we need to do, now we need to do the two stability checks, main stability checks. What are the two main stability checks? External stability checks. What were the two main external stability checks that we need to do? What were the two main external stability checks that we need to do? One is the sliding check, another is the overturning check. So that those things we need to do. So what is the force weight times the friction coefficient, right? So what is the weight of the reinforced soil block? Gamma r, the unit weight of the reinforced soil block, times height times L into tan of the friction between the uh, reinforced soil block and the soil, right? So we have 18. Now see, now what is this length? Now what is this length? This length is nothing but this, right? This is L. It is told that it is as the length to height ratio, minimum it should be 0.7. So you can take 0.7, 4.9 meters. Okay, that's why you take this at this is 4.9. Okay, so this will come out as 617.4 tan 25, approximately 288 kilonewton per meter. And 1025, this 25 friction angle, this is also given to us. Okay, now therefore factor of safety in sliding is nothing but 288. This is the what? This is the resisting force, the frictional resisting force that is developed at the base, and divided by the what? Disturbing force. Disturbing force is what? The lateral earth pressure, P1 plus P2. This value 172.1. 1.67 is greater than 1.5, hence it is acceptable. All right, now next we have the overturning stability. So what is the stabilizing moment? The stabilizing force times the lever arm. Now what is the stabilizing force? The stabilizing force is nothing but the weight of the reinforced soil block. So weight times what is the lever arm? So this weight is acting here, right? So the distance from here, that is the lever arm. So weight times L by 2. Did you already calculated? Okay, this is the stabilizing moment. Like this is the stabilizing moment. Now what is the disturbing moment? The disturbing moment is coming from what? From the earth pressure, lateral earth pressure. That is the disturbing moment. So P1 times h by 3 plus P2 times h by 2. Therefore, factor of safety in overturning, how much? 1513 divided by 442 will come as 3.4. It is greater than 2, so it is acceptable. Done. So these two are done. Next, what is the third external stability check? What is the third external stability check? That is the bearing capacity check, isn't it? The bearing capacity check. Now, for that, what we will do, we will first find the eccentricity. So, what is the eccentricity? Overturning, uh, mm, the disturbing moment or the overturning moment. Let me use this nomenclature. The disturbing moment divided by weight plus Q times L. Q is the surcharge. Okay. Then what? 442 or 443, whatever, divided by 617.4 plus 15 into 4.9. So it will come out as 0.64 meter, and you should ensure that this is less than L by 6. Okay, so it will be less than L by 6. So no issues. So effective length is equal to L minus 2IC is 4.9 minus 2 into 0.64 is nothing but 3.62 meter. Okay, so therefore this one will be 1.91, not 1.9, sorry, 1.91, we'll find it out, we'll see, 3.62. Therefore bearing pressure is 18 times 7 plus 50. This is the oncoming bearing pressure. Okay, oncoming. So 18 is the unit weight times 7. 7 is the what to say, the height, plus 15 from the Q, that is the surcharge, times 4.9 by 3.62. So it will come out as 191 kPa. The airport factor of safety bearing is the bearing capacity. It's given in the question. It's already given to us. The bearing capacity is 600 kilonewton per meter square. So just put 600 in the numerator. So it will be 3.14 is greater than 2 is safe. Okay, done. So like this we calculated the external stability. So first we check the sliding check, the overturning check, and the bearing check. So with that we completed the external stability checks. Now what we need to do, now we need to satisfy the internal stability criteria. So what does the internal criteria say? The internal stability criteria says that we should not, like, the reinforce should not pull out, right? The pull out criteria should be satisfied, and also the rupture criteria should be satisfied, right? So the rupture criteria is satisfied by the spacing of the reinforcement, already saw in the previous discussion, right? The rupture criteria is satisfied by the spacing of the reinforcement, and the pull out criteria is actually satisfied by the embedment length, right? So all those two things we are going to do now. So what is the total horizontal pressure that is coming? Gamma H from soil plus sigma, so not gamma, sigma H from Q, right? So sigma Z Ka R reinforced u k a r. So remember these problems that I am solving, these are quite simple, right? This does not consider the seismic forces and all those stuff, right? But as I told in the previous discussion also, that please try to resolve these problems by considering the seismic forces and all other stuffs in the way that is being done, okay? The way it is solved in the classes, okay, in the main class, okay, in the main class that is uploaded in the NPTEL portal. Okay, try to resolve these problems considering those all other factors. Okay, therefore K, what is our Ka reinforced soil, Ka for the reinforced part of the soil, 32 by 2. So this is nothing but 0.3. Your sigma h is 18 times z at any depth z, 2.31 plus 15 times 0.31. So what is our sigma h? 5.58 z plus 4.65. This is my sigma h. Now my my design tensile strength is nothing but SV times sigma h by CR. Okay, the CR is nothing but the coverage ratio. The design tensile strength is nothing but the allowable divided by the factor of safety. That is my design, right? And this one we're dividing by the coverage ratio. What is coverage ratio? In out of plane direction, the geogrids are placed at some gaps. So there is some slight gap between two sheets of geogrid. That's why we are using this coverage ratio. Okay, so from here we can write 28.6 is given. Right, so from here you will get SVS is my SV. Now in the question it was told that the SV is kind of restricted for us. Why is it restricted? It is restricted because the height of each of these blocks is around 1 meter. Around 1 meter, the height is the weight of each of height of each of this precast concrete facing block. Okay, so our spacing is kind of restricted. Okay, so let us see for 1 meter spacing safely safely till what depth we can put. 1 meter spacing can be put till what depth safely. Let us check that first. So if you put 1 in this equation, 1 to 2.9, from here you will get is sorry, ZS 3.27 meter. So this means that till a depth of 3.27 meter from the top, you can provide a spacing of 1 meter safely. But for lower depths, because the pressure is higher, we will need to reduce the gaps, reduce the spacing. Okay, we need to reduce the spacing. So now let us say if we provide 0.5 meter spacing, then what is the thing? Till how much depth we can go? Let's check. Right, we got 7. That's why, so fine, right? So our the height of our wall is 7 meters. The height of our wall is 7 meters, so we are seeing that if you provide 0.5 meter spacing, safely we can cover the total height of the wall, isn't it? Right, so 7.2 7.3 meters is safe. That's why for 7 meter obviously it will be safe, right? Now what we're going to now to see how we provide the spacing. So we have 7 meter height, right? 7 meter height. 7 meter height. So 1 2 3 4 5 6 1 2 3 4 5 6 7. Okay, right. So 7 meter height of the wall. Each block is of 1 meters. Okay, each block is of 1 meter. And so this is the top of the soil. So what we can do, mm, yeah, so we are saying that we will provide 0.5 meter spacing, right? So let us start from here. So this is the base, right? So this is the first layer, 1 2 0.5 0.5 3 4 5 6 7 8 9 10. Oh, sorry. Yeah. So see, that was what I was saying. So we saw that till 3.23 meters approximate depth, 1 meter spacing is sufficient. So up to this much. Okay, so 1 2 3, yeah, 3. So here we can provide 1 meter spacing safely, right? So let us provide for the upper 3 meters. We can provide little higher spacing. Okay, little higher spacing. So let us mark the reinforcement 1 2 3 4 5 6 7 8. I did some mistake or what? Yeah. This is not a reinforcement, right? This is not a reinforcement. From here you are starting. 1 2 5 6 7 8 9 10 11. Okay, so 11 layers of reinforcement. So all these are 0.5 meter. Okay, 0.5 meter spacing, and here we have 1 meter spacing. Okay, 1 meter spacing, and the top layer we are putting at 0.75 meter spacing just to accommodate properly. Okay, top layer putting at 1.75 meter spacing. Okay, so this is how we are arranging the geogrids. All right, this is how we are arranging the geogrids. So one more thing, see, for these top layers, this, the reinforcement is kind of connected eccentrically to the facing block, right? So if this is the facing block, it is kind of connected here a little bit slightly down. So there might be some eccentric movement. This eccentricity of the connection between the facing block and the reinforcement. There is a tendency that due to the the eccentricity, the facing block might move like this, right? Might move like this. So for that, we will provide some small strips like this. Okay, some small reinforcement strips we can provide like this. Okay, just to counteract the eccentricity issue. Okay, just to counteract the eccentricity issue, we can provide like that. Okay. So this is how we fix the spacing. Now next we have the length. Now what is the length of the reinforcement? So see, we have the active wedge like this, right? We have the active wedge like this, then this part will be our embedment, and this is the LR. LR. So LR, same whatever we solved in the previous session. LR plus LE. So now this LR, how LR, you know how to find out. LR easily we can find out from the geometry. From the geometry of the system, we know this angle 45 plus 5 by plus 5 by 2, so this will be 45 minus 5 by 2. From there, from the geometry, you can easily find it out. From that, easily you can find it out. But how to find the LE? This is the embedment length. How to find the LE? Now, to find the LE, what we do, we equate the forces that is coming to the shear resistance that develops. Okay, okay. So SV times spacing times the horizontal pressure that is coming times a factor of safety. Times a factor of safety just to increase it, right? Just to increase the factor of safety so that you get higher LE. Just to be on the safer side. Okay. Okay, we can that's why we multiply that this with the factor of safety just so that we can get a higher conservative value of the embedment length. Okay, so what is the SV? SV is a variable. We put SV. What is sigma h? 5.58 z plus 4.65. Factor of safety we can take 1.5 for this. Then we have 2 EFLE, right, times CI. Now CI is the interaction coefficient. So when you uh, what to say, if you remember, when we placed a geosynthetic directly, it was twice Le sigma v tan delta, right, like that, like this we have written. But when we use a geogrid, there is some interaction factor or interaction coefficient that we have to use, which defines the interaction between the aperture, because there is a hole, there are holes in the geogrid, right? There is a aperture between the aperture, the soil, and the material of the geogrid. So that actually defines the interaction. This coefficient actually comes from the interaction between all those stuff. Okay, that from there we get the interaction coefficient, and which is determined experimentally. Okay, so this one it's given as 0.75, right? Yeah, times sigma v is nothing but 18 times z. 18 times 18 is the unit weight, times z is the depth, times tan delta. Tan delta is the friction coefficient, right? Now since the aperture between the geogrids are big, we consider that there is soil to soil interaction, the soil to soil friction that is going to dominate. In case of a geotextile, what we considered? We considered the friction angle between the surface of the geotextile and the soil, right? But in our case, in this case, since there are apertures in the geogrid, we are going to consider the soil to soil friction angle only. That is directly we are consider the friction angle of the soil. Okay, so we are going to consider tan of 32 times the CR. It is 0.8. It's also given. The coverage ratio, right? CR is the coverage ratio, since all of the out of plane direction is not covered by the geogrid. So from here, if you rearrange the terms and if you write, you will get LES. So finally, we can write LES 0.62Z plus 0.516 Z times SV. Okay, so this is the LE. And what is the LR? What is the LR? LR we get from the geometry, right? Geometry of the wall and the this active soil bench, isn't it? That from there we get the LE. LR, sorry, LR. So LR is nothing but okay, so we have 7 minus Z 10 45 minus 2 by 2 at LRS 3.88 minus 0.54. Okay, now let us calculate the length and stuff. All right. Screen. Yeah. Better to share a window, right? Yeah. Yeah, so similar to the previous session, whatever we did, we are going to write everything. So we have first we have what? We have the layer number, then we have the Z in meters, that is the depth, then we have the spacing in meters, then we have the embedment length in meter, then we have the minimum embedment length that we have to consider, that we have, then we have the LR in meter, then we have the L calculated in meter, then we have the L required. Just edit this a bit. Okay, so what are the layers? 11, 10, like that, it will go up to 1 layers. Now Z, for the first layer, the depth we gave as point. We have 1, 1, then all are 0.5. Okay. Oh, sorry. Ah, this is the SV, right? Now what is the depth? 0.75, then we have 1.75, then we have 2.75, then we have, oh yeah, 6.75. Okay. Right, so this is the depth, these are the depths, this is the spacing, then LE. Now what is LE? We already find out the expression is equal to 0. Sorry, 0.62 Z plus 0.516 times SV by Z, SV by Z. Yeah, so you get. So what was the LE minimum that we need to have? What is the minimum length? Minimum length should be 1, right? Minimum length is 1. Okay, so if LE is greater than LE minimum, then we will take LE. But if LE is less than LE minimum, we need to take the minimum, that is 1. Right? Done. Now what is the LR? LR 3 equal to 3.88 minus 0.554 times Z. Done. Now LE calculated is nothing but this plus this. We are adding with LE minimum, since that is the minimum you need to give. Okay, so what we can do maximum, for easy, if you want to make it quite easy, what we can do, the whole height you can provide 1 meter, that will be sufficient. Or if you don't want, you can just manipulate it or adjust as per your as per your engineering judgment, whatever however we did in the previous class. Okay, that way you can do that. Okay. All right, so you can go to the PowerPoint. I will just what I'm doing is I will just copy this. Just give me 1 second, right? I'll just copy the table into the PowerPoint, main PowerPoint, right? Just copy it there so that it's easier for you to look at later. I'll just copy this table. Just copy this. Paste it. Okay, we're done. We're done. We'll just stop sharing here, and then we'll start sharing from. Okay. We'll just start sharing from the other place. Just a second. Mm-mm. Share screen. Yeah, so this is what we designed, right? This is what we designed, right? So one more thing you need to check at the end is that you need to check the yeah, you need to, what you need to do is that in the end you also need to check the design strength. Okay, the connection strength, we are not doing it. Connection strength must be checked. The T connection should be greater than or equal to the T design, that is it should be greater than equal to 28.6. So this you must ensure. All right, so this you must ensure. Okay, so this is blank, we don't need this. Okay, so this is how we designed. Okay, so how do you, when do you, how do you decide that you are going to design whatever you have as an embankment, reinforced embankment, or a reinforced wall? That is the question. How do you decide that you want to design whatever you're designing as a reinforced embankment or a reinforced wall? So this is a question, right? So for slope steeper than 70 degree, we design as okay, and for slopes shallower than 70 degree are yes slopes. All right, so there are various cases where slopes might be designed or the embankments are designed, right? So one is the when the slopes are situated on weak foundation soil, right? So this is the embankment, say, and the soil, this soil is particularly very weak, the foundation soil is particularly very weak. In that cases there are chances that the foundation is going to fail. So this foundation is very weak, very soft clay, very soft soil, then this foundation is going to fail. In those cases what we need to do, we need to strengthen the foundation using various means. So in the next we will see, in tomorrow session we will see how we can use geocells to actually construct embankments or over soft soils using geocells, where the geocells are used to actually increase the strength in that cases. All right. And the next case can be when the slopes are very steep, the foundation is strong, there is no chances of the foundation failure, but the slope of the embankment or the slope angle is quite steep. In that case, what we need to go for the planar wedge analysis, the slip circle analysis, the bilinear wedge analysis. With that, we need to actually decide what to do. Okay. Now, which shear strength property that you are going to use for slopes which undergo large deformations? So the slopes which are generally situated over very soft soils, they generally tend to undergo very large deformations. So in that cases, what we do, we use the constant volume strength parameters. Okay, so if we plot the shear strength with the say strain, we get something like this, some graph like this. So this is the peak value and this is the what, constant volume value here, or the critical state or the constant volume value. Okay, critical state value or the constant volume constant volume strength. So when the deformation is actually large, right, when there are chances that there is going to be large deformations, we tend to use this value to find out the shear strength parameters. Okay. Okay, so these the parameters calculated using this residual or the not residual, the constant volume, the shear strength, the cn5 value is calculated from there, is more appropriate than that from the peak values. Okay. Now these things are actually already discussed in the class, so we will just go through a bit, just overall we will see what is there. So first is the basal design of basal reinforcement. So what is a basal reinforcement? The basal reinforcement means, say you need to construct a slope or you need to build a slope or an embankment. So initially it just so that the construction equipment and all those things can move over the mean base ground. What we need to do to strengthen its base, strengthening the base ground, what we need to do, we generally use the basal reinforcement. Okay. So this is the basal reinforcement that we use. So you can see here, if the friction angle is 0, if the soil is completely cohesive soil, then what is the factor of safety? The factor of safety is nothing but Cu times La times R divided by W into X. So what is Cu times La? Cu times La is nothing but the shear resistance that develops. Cu is the undrained cohesion of the soil times the length of this R slip circle. That will give the shear resistance times the R. R is the what, radius. So R is nothing but the lever arm. So Cu times La times R will give it the resisting force and the weight. So and this soil mass actually has some weight. So due to this weight, this slope failure is happening, right? Due to this weight, the slope failure is happening, right? So that weight times the x. X is nothing but the distance of the centroid of that weight from the main radius, that center line, right? So that will give us the disturbing force, right? So Cu into La into R, W into X, done. So we get the factor of safety. So now if when this is the case when there is no reinforcement, but when there is a reinforcement that we use, at that time this extra part will come, right? The moment due to the reinforcement force. So there is some force that is going to, resisting force that will get generated on the reinforcement, which is going to prevent the sliding of the slope, sliding failure of the slope, that is going to prevent. In that case, the moment from that reinforcement force, that is going to add up. Okay. So what happens if the, now this is the case when this reinforcement is quite rigid, right? Now what happens if the reinforcement is flexible? When the reinforcement is flexible, what happens? There is a kink. A kink actually develops here at the interface between the slip circle and the behind the whatever the soil is there. Okay. In that case, what we do is that we actually in that point we consider that so this kink actually develops like this, right? So we consider that the resisting or the resisting force due to the reinforcement actually acts like this. Okay, at that point along the slip surface. right? So finally what we do, finally we need to determine the strength of the reinforcement that we need to put. So this is what we do. The strength of the reinforcement is nothing but FSR minus FSU divided WX bar by lever arm. So FSR is the factor of safety when the reinforcement is used. This FSU is the unreinforced case times WX bar by lever arm. Okay, this will give us the maximum or the required tensile strength that the basal reinforcement must have. Okay, it will give the minimum design strength that the basal reinforcement must have. Okay. So this was the case for what? Uh, Phi soils, sea soils, right? It's completely cohesive soils where we don't have any phi or friction angle. Okay, we don't have any phi. It is completely fully cohesive soil. Now, what if the soil is a C5 soil, cohesive frictional soil? What if the soil is a cohesive frictional soil? In that case, what we need to do? In that case, to calculate everything, what we need to do, we need to do this wedge analysis. Okay, this wedge analysis we need to do. We need to choose a slip circle, then we need to consider divide the soil in certain wedges. When wedges, we need to divide the soil in various wedges, and for each wedge we need to do so. If we see here, this is the factor of safety for reinforced case. So first term, what is the first term? C prime into LA into R. It is nothing but the free resistance coming from the shear resistance that is developed from the cohesion that is coming from the cohesion of the soil. Right, this is coming from the cohesion of the soil. C prime LA into C prime is the cohesion of the soil. LA is the length of this R times R. R is nothing but the radius. Right. Next, the next term is nothing but what is coming from the cost component. So there is some sine component of the weight and it's the cost component of the weight of the wedge. Right. So say this is any wedge weight downwards. That weight is having a sine component, the cost component. The cost component will be giving the normal force. So the normal force times the 10 friction angle gives us what? The frictional resistance. Normal force times the friction angle times the 10 of the friction angle gives us the resisting shear resistance, right? So tan of the friction angle you have written here times the normal force. Normal force is what? Wi summation is there because many wedges are there. So Wi cos alpha I minus Ui I, that is coming from the pore pressure, pore water pressure. This is coming from the pore water pressure, right? Summation of that times the R. R is the radius plus the whatever resisting force it is coming from the reinforcement, these reinforcements. Okay, any number, whatever number of reinforcement we have, that number plus the summation of that Pi times Yi. Y is the distance from this to this. Okay, Yi divided by the disturbing force, disturbing moment. What is the disturbing moment? The disturbing moment is from the sine component of the weight. So summation Wi sin alpha I R times summation sin, right? So this is all. Next, one more thing we can follow is the slip circles analysis using the Bishop's method. In Bishop's method, you can see that this is the expression that is given, okay, for the unreinforced soil and for the reinforced soil. These are the expressions that are given, okay, for the unreinforced soil and for the reinforced soil. This is by the Bishop's method. Okay, so here you can see you have the factor of safety term on the both the sides. You have the factor of safety term on both the sides. So in that case, what we need to do, we need to assume a factor of safety. We need to assume a factor of safety. We need to put on the right side. Then we need to calculate the factor of safety. If that is equal to whatever we had assumed, then that is fine. Fine. Else what you do, whatever you calculated, you use that again on the right side. You calculate again and you keep on checking whether the LHS and RHS both are equal. When the LHS and RHS both are equal, that means that is the correct factor of safety. Okay, so a bit of trial and error method you need to do here. Alright, a bit of trial and error method you need to do. Yeah. Now this is one more case. This is the case for steep slopes. For steep slopes, how you can analyze the factor of safety, sliding factor of safety. Okay, the factor of safety. So here you can see you have a steep slopes of angle beta that we have considered. We have surcharge at the top, right? We have surcharge at the top.
and AC is nothing but the rupture plane. So here we are, in this case we are considering a circular way, circular slip circle we are considering, but here we are considering a wedge instead of an arc we are considering a wedge, planar wedge we are considering. Okay, that is the difference. So all the other stuff is given to us. I am not going to repeat again and again, everything is given here. So you can see everything, all these things already discussed in the class, and it is also quite clearly, all the terms are clearly defined. What is the rupture plane, the slope angle, the vertical force, what is the vertical force, the normal force, the shear resistance, the resistance from the reinforcement forces, all these things you consider, and then you calculate the factor of safety. Okay, so I am skipping this part, not just repeating this for brevity. You can go through the class lectures again and again. There, completely everything is defined. Okay, clearly. Yeah. So yeah. So let us. So we have around three problems to solve. So these are easy problems. Okay. I think three more problems we have that we are to solve. Quite easy problems, we will solve them easily and slowly. So these problems are quite similar to whatever we solved for the we solved some problems in the first second in the previous class also, so similar to that regarding this sleeps wage and all. So just give me 2 minutes. In the meantime, you just go through the question, and then we will start solving the problem. Okay. In the meanwhile, while I am away for 2 minutes, just go through the question. The question is quite massive, big question. So just go point wise. What are the points A, B, C, D? Four things that is actually asked. It is being asked us to solve. Just see this. Okay. Just try to read the question and just try to start by yourselves. Start solving the problems by yourselves. Okay, and I will catch up with you in a few minutes.
Yeah, so I hope you have gone through the question. So what is asked actually? What is what is asked in the question? Assume you are dealing with 10-meter high 50-degree angle embankment shown below. We'll see the figure, okay? We'll see the figure. It consists of a silty clay soil. Unit weight is given. All the parameters are unit weight is 19 kilonewton per meter cube, phi 0 degrees. Or there's only C is there, phi 0, right? So cohesive soil. C is 15 kPa, area is 60 meters square, center of gravity is integrated. In the figure we will see all this stuff is given on a silty clay foundation. Okay, so at 10-meter high 50-degree embankment is situated on a silty clay foundation. The properties of the foundation are also given, right? Unit weight is 20 kilonewton per meter cube, phi is again 0 here also for the foundation. C is 18 kPa, area is 55 meters square, center of gravity is integrated. We'll see what are we asked to find. A, determine the factor of safety with no geosynthetic geotextile reinforcement. Okay, when there is no reinforcement, we need to determine the factor of safety. Determine the factor of safety with a geotextile of a allowable tensile strength of 40 kilonewton per meter placed along the surface between the foundation soil and the embankment soil. Okay, only one layer of geotextile reinforcement is placed between the foundation and the our slope embankment soil. Okay, then determine the factor of safety with 10 layers of the same geotextile placed at 1 meter intervals from the foundation interface to the top of the embankment. Okay. Assume that sufficient anchorage behind the slip circle shown is available to mobilize full geotextile strength. Discuss how the problems. Okay, we'll see that. First, unreinforced, we need to determine the factor of safety. Then one reinforced with only one geotextile. Then 10 layers of geotextile, and then we need to discuss how would we solve if the soil was C5 or 5 only instead of uh, this. Okay, just 5 soil. All right. Okay. Yeah. So this is the slope that is given to us. Okay, this is the slope. The embankment soil properties are given. The foundation soil properties are given. We need to find out keep on calculating the factor of safety. First for the unreinforced, then for the reinforced, and again for the multiple reinforced. Okay. So let us see. So what is the weight of AB? Weight of ABED. That weight let us first calculate. Weight of ABED. Okay, this part. The weight of this part is what? 19. That is the unit weight times the area. Area is given 60. Weight of the lower part, this part, right? Now these are the weights that we calculated. Now what is the length of this AD? Can you calculate? Can you calculate the length of AD for the basic math of 2-3 standard math, class 2-3 standard math? So angle is given. The angle is given. You have to find out the arc length, AD. How do you do that?
Okay, so it will be twice pi into 21 into 34 pi. Now this arc length we need to find out next. Same. Okay, so we calculate the weights of this and also the arc length, right? Now what is the factor of safety? Initial unreinforced factor of safety. Summation of resisting moment, overturning moment by, resisting moment by overturning moment, right? So what are the resisting moments? How to calculate the resisting moment? C embankment. C embankment times LAD plus C foundation times LDF times R, isn't it? Times R divided by, right, from here to it's given 12.5, and for here CG is here, right? It passes through the center, so 0 lever arm. Just put the values. This will come out as how much? Calculate. 13620.96. Not acceptable. Right, it is less than 1. That means the slope is not stable only. It's right. It's going to fail. The slope is not going to stand on its own. It's going to fail. Right. Now, the second part of the question, it is asked that if there is only one reinforcement here, if there is only one, I will erase other things. If we have one reinforcement here, then what is the case? Then what will happen? So how to do that? What was our resisting moment? 13620 plus a term will come from the strength of the reinforcement, right? Plus T into Y by same T is given as 40. Where is it? Given as 40. This is still not, just to say, this is still not acceptable. This case also still not acceptable. Now let us see. If we provide 10 reinforcements, 10 layers of reinforcement, what will be the case? So what is the same? Plus now we have to summation Ti yi 0 So plus Ti is for T. T is same for all, but the heights are going to change, right? Because see, like this, like this, like this, 10 reinforcement you are going to apply. So from here, the Y value is will be different for all the layers, for all the layers. So 17 plus 16 plus 15 plus 14 plus 13, 1 meter at 1 meter spacing we are providing, plus 11 plus 10, 2 3 4 5 6 7 8 9 10. Do this, calculate this while I erase that all the stuff. You try to calculate this, please. Try to calculate this. One, two, three. Try to calculate. This will be. It's also marginally acceptable. Marginally acceptable. So what can we do? So what we can do? We can increase the strength of. You can provide a higher strength of reinforcement, higher strength reinforcement, or you can increase the number of layers by reducing the spacing. All these adjustments you can do in order to increase the factor of safety. Okay. Now we had a fourth part of the question also, right? So what if the soil? What if the soil was a frictional soil? In that case, how would we solve this problem? In that case, we cannot solve it this way, right? So we have to consider the wedges. All the wedges you need to consider, multiple slip circles, and you need to consider the wedges, all the wedges, and from wedges, or considering the wedges, the normal force, the frictional force, all these things, whatever you saw here. Like this, we need to solve it, right? By considering wedges. Okay, for frictional soils. All right. So this is a very tedious process. So many softwares, commercially available softwares are actually available, which will actually do this rigorous computation for you and give you the factor of safety. But it's okay, completely fine to use these softwares, but you should know what is happening inside, right? You should actually know what is happening inside. Okay, now let us see this problem. This is pretty easy. You should be able to do it by yourselves. It's very easy, very easy, very simple problem. Try to do this. With reference to the previous problem, determine how much embedment is required behind the potential slip circle in order to mobilize the allowable tensile strength of the geotextile. Assume that the transfer efficiency of the geotextile to the shear strength of the soil is 0.8 and base the calculation on a factor of safety of 1.5. Determine the total length of the geotextile using the maximum distance from the slope face to the failure plane to be 8 meters. So what is the question? So we have this slope, right? Okay, so we have some failure wedge like this which is going. So we are providing a geotextile reinforcement like this. Okay, we are providing a geotextile reinforcement like this, and it is given that from here to here it is 8 meters. Okay, 8 meters. What we need to do, we need to find out the how much embedment, how much is this length that you need to, embedment length that you need to provide. So use the basic same concepts that we used in the reinforced earth walls for the today's class also. Just today's class we solved the problem, in the previous class also we solved the problem. It's the same concept, how to calculate this embedment length. Please try to calculate that. Please try to calculate. Please try to calculate this. Give me a minute, I will take a call. In meanwhile, you please try to calculate this. It's very easy. Directly you have to calculate, you know already how to calculate the embedment length, right? So you need to equate the mobile shear resistance to the allowable strength. You can equate, and then you can find it out, right? Just equate the shear resistance that is mobilized to the tensile allowable tensile strength, then you will be able to find it out. Just try to calculate this. Yeah, right. So just equate the equate your basic what to say, equate your frictional resistance to the resistance that develops between the at the top and the bottom surfaces with the strength of the geotextile. Simple. Okay, 2 times what is the frictional resistance, that will be nothing but the what, see equation, where is that equation, that is 15 degree, as it is a completely cohesive soil, 50 15 here, 15 kPa. E is the efficiency, transfer efficiency that is given. Alive, it's 40 times 1.5, radius 2.5 meters. Therefore, total length, okay, here understood, right? Here we don't have to do 2 into normal force into 10 5, because it's a completely sea soil, we are using direct force. In place of this, we are using the sea level. But 0.5, done. Simple, right? Very simple. Sorry, what did I do, man? Yeah.
Now let's go to the next problem. Actually, we have time. There is nothing, not many problems. So we are almost done. We already are towards the end of today's session. Okay. Maximum it will take 15-20 minutes more. Then we'll be done. Okay. Yeah. So let us see this question. For a failed slope of known centroid in radius resulting in a resisting moment of 2010 kN per meter and a driving moment of 2570 kN per meter, determine A. The factor of safety without the reinforcement. B. The number of layers of a specific geogrid with an ultimate tensile strength of 78.7 kN per meter and combined reduction factor of 11.8. Average center of the reinforcement is 14.3 required. Very easy. Similar problem. There's two things we need to do. We need to determine the number. First, we need to determine the unreinforced for the unreinforced slope. What is the factor of safety? And next, we need to calculate the number of layers required for the reinforced slope. Okay. So let us do. Let us do that. Unreinforced case. So what is factor of safety? I am resisting by I am disturbing. So resisting moment is given as 2010, and what is disturbing moment? So obviously you can see this indicates failure. Alright, this indicates failure. Allowable. Right? Ultimate is given divided by the cumulative reduction factor, which is given as 11.8. Get this as cumulative reduction factor. I hope you remember multiplication of installation damage, chemical biological damage, all these things, creep, all these things, all this reduction factor. If you multiply all those things, we will get the cumulative reduction factor that is directly given as 11.8. So 78.7 divided by 11.8, we get the allowable order design as 6.67 kilonewton per meter. For factor of safety is resisting since we have multiple layers plus n number of layers. Since all the layers are going to have the same reinforcement, the reinforcement having the same strength, we can bring it out of the we can write it like this, right? N into T allowable into Y average. So Y average is nothing but the average centroid of all the reinforcement is given. Right? N times T over N number of reinforcement into the allowable times the Y average. Okay. By T allowable, Y average is given in the question. Two 570. So please do this. Find N from here. Find the n value. How many number of layers? What is the n value? What are the number of layers? How many number of layers?
17.
Yeah, 17. Right? So 17 number of layers we need to use. Okay. Very simple. These problems are really very simple. Nothing much. Just basic. These are for clearing up your basic concepts. That's it. Okay. All right. So now let us go to the last problem for today's session. This one. Okay. This will be problem 5. 5. Okay, I hope the numbering is correct. Please correct it yourself. Okay. So what is the question? We plan to construct a soil embankment at a 70-degree slope angle with the horizontal and 10-meter height to be reinforced with unidirectional geogrids having ultimate strength of 180 kilonewton per meter and a combined reduction factor of 4.12. So obviously ultimate you have to divide by the combined reduction factor, we will get the allowable, right? The factor of safety is to be 1.4. That is given. The soil is granular with unit weight 18 kilonewton per meter cube, phi is 30 degrees, and a no pore pressure. That is RU. RU is 0. That is we have no pore pressures. That is to be considered. Okay. No pore pressures. As it is a granular soil, we are considering the all water will be drained out, so no pore pressures. Okay. Determine the number, spacing, and length of the individual geogrid layers. Okay. So, what is this RU? RU we say you have a slope, right? Like this, you have reinforcement layers. So at a surcharge here, say any depth Z1, say at any depth Z1, RU1 is nothing but U1 by sigma Z1, and at again at any depth say Z2. Okay, any depth Z2 we have RU2 as U2 by sigma Z2. So RU is nothing but the ratio between the pore pressure and the geostatic or the pressure, total stress. Okay, sigma gamma into Z is nothing but the total stress that is coming. Okay, that is what here. In our case, it is given that this RU is actually nothing but 0. Okay, RU is nothing but 0. Now, in to design this, we will be using the Jewel's method. Okay, to design this problem or to solve this problem, we will be using the Jewel's method. So now Jewel actually gave some design charts. Jewel actually gave some design charts for various pore pressure ratios. So in our case, the RU is 0. So we will be using the design chart for RU is equal to 0. Right? We will be using the design chart for RU is equal to 0. So you can see this is the chart, steep reinforced slope design chart. So since, so what is the slope? The slope is 70-degree, means this angle of the slope is beta is 70-degree, means quite slow. If it's more than 70 degrees, what we do? We design it as a reinforced soil wall, isn't it? We design it as a reinforced soil wall. But since it is 70-degree, we can design it as a reinforced slope, and the slope is will be considered that we are considering is a steep slope. Okay, this is steep slope. Now for the steep slope, Jewel actually give the some design charts to make our task easier. Okay, so we'll take help of the design chart. So you can see the name of the charts are steep reinforced slope design charts, right?
Only for steep slopes you can use. Only for steep slope you can use this. Okay. Now we have RU0, so you are using the chart for RU as RU equal to 0. Now you can see this chart has three graphs, right? Three plots. The first plot gives us the minimum required force. Okay, the minimum required force is given by the first chart. So minimum required force is nothing but the what to say? Uh, mm, how do I define that? The minimum force for which the reinforcements are to be defined. That's why it is known as the minimum required force. Okay, this is the minimum force. The basic, the you have to design at least for this force. Okay, at least for this force we have to design. That's why it is known as the minimum required force. How to use this k required, the minimum required force, we will see that. Okay, okay, this is for the first chart, first graph. The second is the length requirement. So LR by H overall, considering the overall stability criteria. So there is a overall stability criteria and one is the direct sliding because of the sliding. Okay, so you have two criteria. One is the overall stability of the complete reinforced slope, and other is the sliding direct. So this is the reinforced slope, right? So this is the reinforced slope. So some soil is there here also, some soil is there. Due to this soil is actually giving some lateral pressure, earth pressure to the slope, So the it so we need to ensure that due to the uh, wait, yeah. So you need to ensure that we need to ensure that due to the lateral thrust coming from this backfill, this soil, the reinforced slope does not completely slide, directly slide due to the lateral force that is coming from the this soil. Due to this soil, whatever force is coming due to the lateral force, whatever it is coming, this should not directly slide. Okay, that is ensured by selecting this thing. Okay, so from these two, what we get two lengths of this. So I will just draw here. So this is the slope, right? So this is the reinforcement. So this is the length of reinforcement, right? This LR, what is given by these two graphs. This LR is given by these two graphs. Now what let us do, what we can do it from the graph. Let us see, our angle is beta is 70 degrees, right? Our beta is 70 degree. Now for beta is equal to 70 degree, what is the values that we are getting? So from here, so this is for 30 degree, for 70, like this it will go here, right? Here, so here, approximately here. So k you can take, k required you can take is 0.19, say approximately from the graph. You can take it as 0.19. Now from here again we have to do. So this approximately you can take 0.51. Overall it is 0.51, and the last one from here, what, this PowerPoint is such a bad software. See, like this, right? So from here we can take approximately 0.38. So LR by H direct sliding is 0.3. So this we got. Now, yeah, now what we need to finalize, we need to finalize the spacing. So how to finalize the spacing? is given by GL. Okay, the spacing is nothing but T designed by K required into gamma times Z max. It is at maximum depth. So here we will just put K T design is what? 331.2 is given. Right. So T design, how to find? How to find T design? T ultimate by 4.12 for T design. Okay, by unit weight is given 18 by Z max maximum depth. Z maximum is going to be nothing but 10 meters from here. So this one will come out as 0.9. So if we provide the even spacing, means all spacing are equal, then say if we provide even spacing, then total numbers of layers n is equal to how much? Height by spacing 10 by 0.91, approximately 11 layers. Okay, so 11 layers you can provide it equal spacing of 0.91 meters. Okay, now to select the length of the reinforcement, this length LR that I was saying, this LR, there are some criteria. Okay, what are those criteria? Let us see. If LR by H overall is greater than LR by H direct sliding, then use LR by H overall constant length throughout. Okay, and again, if not, if this criteria is not, if L overall is less than LR by HDS, then use LR by H DS throughout. Okay, you can use LR by H. So if LR by H DS is greater than LR by H overall, then you can use this LR calculated from LR by H DS throughout, or what you can do, or vary. How vary? Say this is the slope, right? This is the slope. So now let me draw it in another way. So this is the slope, right? So here you can give, at the bottom you can give LR by H ds, the top you can give LR by H overall. Okay, overall, and you can vary it like this. Okay, vary the height. Okay, vary the height. Okay, you can just vary the height like this. I hope you understand. Like you can just vary the height. At bottom you can have LR by H ds, and the top you can have LR by H overall, and you can just vary that. That's what I meant to say. Okay, or else you provide LR by H by ds throughout. So in our case, what is the thing? In our case, LR by H overall is 0.51 and LR by H ds is 0.38. So in our case, we provide LR by H, we select LR by H overall as throughout. So 11 layers, whatever you will be providing, what you will be doing is, so this is the slope, say, right? So I am not able to draw. You just draw it, okay, yourself. You cannot accommodate here. Try once again though. So this is the soil only. One, two, three, four, 5, 6, 7, 8, 9, 10, 11. Okay, and the this this is same for all. 5.1 meter. Okay, here also at the top also we have 5.1 meter. Okay, so this is how we will reinforce the slope. Alright, this is how we will reinforce the slope. Okay, this is 70 degrees. Okay, total height is 10 meters from top to bottom. So like this you need to do. Okay, so I hope this was clear. So very easy, directly we need to use the given conditions. That's all. Okay. Okay, so with this we will end today's session, and one tomorrow we will have one more session from 3 p.m. to 5 p.m. The usual will in the usual link, this link it will go. So tomorrow we are going to have one more session for 2 hours, and then again from next week everything will be normal. Every Sunday we'll be having. Okay, just today, just the past week and this week there were some disruptions, and hopefully there won't be any disruption in the oncoming weeks. So today we finished the 6th week session, and the 7th week session will be on tomorrow, right? Tomorrow from 3 p.m. to 5 p.m. So yeah, so that's all. So let us meet again tomorrow at from 3 to 5 p.m. And I hope that all whatever we discussed today was clear to you. If you have any doubts, please feel free to ask me. I am here. We have 10 more minutes, so I am here till 8 o'clock. If you want, you can ask me, or if you want to go, you can go anything. But I am here till 8 p.m. You can ask me, and tomorrow again we are going to meet at in the afternoon at 3 p.m. Okay. We'll be trying to solve some basic easy problems from the geocells and other stuff. We'll see those things. That's all for today, I think. Let us see, just see if yes, we have time. We'll leave this, yeah. So what we did, so initially we solved this problem, right? We solved this basic design problem using the geogrids that we started with this problem, right? So this was similar to the previous problem of geotextile that we solved. Yeah, so that's all we did today in the beginning. Then yeah, so try to solve this problems again by yourselves. Okay, just try to solve this again by yourself. I try to incorporate the seismic forces and all these things. Okay, then we saw designer problems, then we solved some easy problems from design of the calculating factor of safety of reinforced embankments. All these things we did. That's all. Yeah, simple only. I hope it was everything was clear to you. So tomorrow we'll meet again from 3 on the 8th of September. Tomorrow from 3 to 5 p.m. We will solve some more problems, right? So thank you so much for attending. If you have any doubts, I'm here. Please feel to contact me. Or I'm here for 9 more minutes. Please feel free to ask me. Okay.